Howdy, welcome back. Today we're going to do a little bouncing around between a couple different presentations. So we're going to start on Chapter 3, and then we'll bounce back to Chapter 8. I'm not sure if my internet's good enough to stream today, so I might have to bounce to Discord, but we'll see. Let me know in either chat if it's too laggy for you. Okay, let's start with this guy, Agile Development Techniques. We'll go from there. Okay, so we didn't look much at Agile development so far, and we're actually going to start somewhere kind of in the middle. We're going to start with extreme programming. Extreme! And we'll talk more about Agile, obviously, a lot more over the course of the semester. We're going to start with extreme programming because it's where this testing first methodology that we're going to be using in this class really comes from. And extreme programming is a lot older than the testing first methodology that we see today. It basically comes from the late 90s. It's a development on top of Agile, which again we haven't learned about too much. But let's look at some of the principles here. First, new versions might be built several times a day. New versions are delivered to the customer frequently, so every 2 weeks, that's pretty often. And all tests must be run for every build, and the build is only accepted if tests run successfully. So this third bullet has become pretty universal in modern software development with the advent of automated testing and the advent of testing suites and smoke tests and all these different things. Having automated testing and other testing run at the end of every build and then delivering the build to production if the tests pass has become a very common part of the continuous integration pipeline that drives modern software. So let's look at the extreme programming release cycle and where we're at in it, because we've been following sort of some extreme programming without knowing about it. So first you're selecting user stories for this particular release. Now, I had you write user stories. You have not yet decided which user story you're going to focus on first, and most of you wrote user stories that are so broad that you almost have to design the whole system before you can actually commit to one. But you select user stories for release, break down what tasks you need to finish to complete those user stories. Then you're going to plan how this release is going to go based on you finishing those tasks. So maybe you distribute those to the team or whatever. Then all this stuff in one step: develop, integrate, and test the software. Then you release it, evaluate it, and repeat for the next set of stories. So we are here approximately at breaking down our stories into tasks. And then we're going to plan, and then we're going to develop and test, roughly. Let's look at a couple other practices of extreme programming, since we're already on it. So incremental planning. Requirements are recorded on story cards and stories to be available in release. Okay, well, we've done that kind of to an extent. We also have a more traditional long-form requirement document, but towards the end we converted it into more of a user story-based document. We've got small releases. All right, so keep that in mind as you go. What is the smallest thing that you can finish in, let's say, the next 2 weeks? So look at the project that you're working on and say, what's the least we could actually deliver at the end of the next 2 weeks? Because we're going to start at least the testing for development pretty soon. So bear that in mind as you're going through your requirements. What's the smallest thing that we could deliver? What's the next increment of value? Simple design speaks for itself. We only design what we need to fulfill the current task, no more. So unlike more traditional planning-based processes, we are not going to create a high-level system design for the whole system. So we are only going to design just up to what we need to create that next iteration that we're going to deliver in 2 weeks or whatever. So this is in contrast to the old school method where you might design the entire system before you even start programming it. Test first development is the thing that we're trying to really emphasize. You need an automated test framework. So after you commit changes to your system, the automated tests run and determine if you have broken anything. This automated test framework is something that we'll look into probably next week or the following. Hopefully all of your choices of language and everything support it. We'll see. Refactoring. All developers are expected to refactor code continuously to make improvements, so we're trying not to pile on tech debt. We're trying to continuously update so that we don't have too many pieces of code that are difficult to maintain, in addition to moving forward on features. But every software development method claims that they do a lot of refactoring in practice. It's not exactly a priority for everybody. A couple of other practices that you see in extreme programming. Pair programming is an interesting one. Actually, all of these are a little bit interesting from a psychological perspective. If you think about why they became popular in business, what is the benefit of pair programming to the company? You might think intuitively, okay, well, if developers are always working in pairs, and in traditional pair programming, one person is writing code and the other is observing, I think, well, really they're cutting their productive hours in half, right? Because instead of two people doing work, you really have one person working and one person checking on them, and that seems like a bad deal for the company. But in practice, think about psychologically some of the things that happen when you have to work in a pair like that. So if you need to take a break, you both have to agree to take a break, because generally when you're pair programming, you're not supposed to continue without your partner. Well, that creates a demotivation to take a break in the first place. Since you always have another set of eyes on you, it's not very easy to just kind of go and browse Reddit or something. That's not going to work. And if you're the partner that's supposed to be observing and you just go and start browsing the internet, well, the partner that's typing is going to be upset with you. And of course, if you're the partner that's typing, then you can't just go browse the internet, because that's going to be pretty noticeable. So pair programming is actually a good way to extract the maximum possible amount of labor out of a set of employees, although not everybody's a big fan of it for that reason. Collective ownership is similar. Everybody is in charge of everything. That kind of raises the overall responsibility of the team. Pairs will work on all parts of the system. This is helpful not just for the obvious kind of teamwork reasons, but also consider that if there's a lot of turnover in the organization, which there is in general in software, and one person has all of the expertise in, let's say, a particular part of the code and they leave, well, that's an issue. But if you have collective ownership, everybody's got some level of expertise in everything. Nobody takes full responsibility for some particular part of the code, then people are more interchangeable. It's okay to lose somebody every now and again, because everybody should be able to work on every part of the code. It also puts a lot more burden on the developers to become knowledgeable in the entire code base. Continuous integration we'll talk about more later, because it's a more complex subject. Sustainable pace. Everybody says they don't do overtime, so great, but in practice, if you're running good software development, you really shouldn't do a lot of overtime, because productivity drops off the more people work. And on-site customer is an interesting one that goes back to that accountability thing. If there's a representative of the end user around, again, it's more difficult to slack off at work, and also, you're being held accountable in the sense that somebody's literally observing you as you develop the system. So there are obvious benefits to that too. You can always ask the customer for input and so on and so forth, but at the same time, the customer always being present is interesting. So incremental development, customer involvement, people, not process, pair programming, collective ownership, avoid long working hours, all that stuff. Not really relevant for today. Relevant and user stories we've already covered, but you should remember these from our previous discussion. User requirements expressed as user stories or scenarios. Sometimes you might want to limit the length of these, so you would write them down in a card to keep them to a paragraph or so. Here's an example user story if you're interested. There's what it would look like on a card. We'll talk about refactoring later. Let's get to test first development. So why do we test up front before we develop the software? Why test first? Writing tests before you write your code makes it more clear what you're going to be writing your code to accomplish. Another way to express that is that you're clarifying the requirements that you're going to be implementing as you write the code today or this week or whatever. If tests are written like programs rather than as data, then your tests can execute automatically. So your tests are actually code too. Your tests aren't just like inputs like 1 and 5 and 4. In test-driven development, your tests are also code. They instantiate objects. They do things to them. They test functions. The test might also include a check that it is finished correctly, and it also probably includes input data, but it's going to rely on some kind of testing framework that allows you to write code within your tests. JUnit is an example. For Java, JUnit's probably what you'll use if you decide on Java for your project. And with test-driven development, you keep your old tests unless they've become obsolete for some reason. So every time you're writing new code, you write your test first, then you write the code. And then you still have all the tests from the previous round of code you ran. And so every time you write new tests and new code, you run all of your tests. And then every time new functionality is added, you make sure that you haven't broken anything before. So all of your tests are running every time you make changes. Now we're going to transition to the other slideshow. Leave behind extreme programming for now. Okay, so let's talk about software testing a little bit and look at what you're going to do today. So why do we do program testing? Why not just write code and forget about testing? So besides the benefits to productivity, testing is intended to show that the program does what it's intended to do and to discover defects in the program before you put it into use. That should be pretty obvious. When we test software, we're going to execute it using artificial data, but sometimes we try to make a close mock-up of real-world data too. Maybe we even test with real-world data sometimes. We can reveal the presence of an error, but we can't reveal that a program is free from error. That's an important thing to note, is that as you're going through and writing tests, you can never really prove, outside of mathematical proof, that a program is completely free from defects. And now let's look at two things that are important here. So to demonstrate to the developer and to the customer that software meets its requirements. Okay, so if the software meets its requirements, you should be able to prove it, right? And that means that for all the requirements that you've written, so everything that you said that you would do in the contract, you need to be able to prove somehow that you've done it. And that's where we come into the concept of validation. So for every requirement in the requirements document today, you're going to go through and say, well, how can we prove that we met that requirement? So we're going to call that the validation document, although it goes by different names. Sometimes it's part of requirements too, but we're going to make it a separate document just for clarity. And what you're going to do today is essentially this bullet. For every requirement in the requirements document, you are going to determine how it is that we might say that we met it, how it is that we might prove it. And then we want to discover situations in which the behavior of the software is incorrect or undesirable or doesn't conform to specification. This is actually what we would probably think of more intuitively when we think of testing. The discovery of defects, of bugs, of crashes. That's not necessarily what we're going to be focused on today. We're going to do that later. So today, think about testing in terms of how do you prove that you've done what you say you're going to do. Validation and defect testing. That first bullet point is what we call validation, the one you're going to do today. You expect the system to perform correctly using a given set of test cases, so you've come up with some tests that reflect that the system is doing what you said that it would do. And then the second goal is you're trying to expose defects. We'll do that later. Again, validation testing demonstrates to the developer and to the customer that the software has met the requirements that you promised you would meet. A successful test shows that the system operates as it was intended, whereas defect testing, you're trying to discover faults or defects, show that the system might be incorrect or not in conformance and needs to be fixed. A successful test is a test that makes the system perform incorrectly and exposes a defect, which you would then fix, which might go into validation testing to show that it's now working as intended. And I think that covers it for today. Let's end on this. So verification versus validation. Verification and validation, sometimes called the two V's, the two questions you need to ask. Verification is, are we building the product right? Is it conforming to its spec? And validation is, are we building the right product? Note the slight difference in the words there has a big difference in meaning. The software is validated if it does what the user actually needs, if it satisfies their goals and everything. The software is verified if it conforms to its spec. So you can have software that completely meets its requirements, is fully up to spec, but doesn't actually do what the user wants it to do. So the purpose of fitting the V's and V's is to establish confidence that the system is fit for what it's intended for. So depending on the system's purpose, user expectations, etc., you got to meet your two V's. All right, taking up enough of your time, so check the assignment on Canvas, go into your groups, and begin your daily task. I will see you in Discord.